All right. What do you say? You start?
Go. Yeah. Morning, people.
Good morning, everybody. And again, we have a small number of people, number one, here live with us, and we'll try to do better next time. And for those of you out there trying to get in, a bunch of you asked to be invited. We've tried to invite you, and we think we finally succeeded. So you should have the invitation, and you should accept it and join the discussion. But for now, we'll just start, and we have one person with us, Fidan. Welcome. Do you want to unmute just for a second and tell us where you're from? If you are talking, we can't hear you. You can type, and I'll read it out while you figure out the logistics. From Baku in Azerbaijan. So wonderful to have you with us. And so what should we speak about today?
I guess we could start with the centipede, or do you want to start just generally? There were a few questions that came up.
Let's do it. Let's start with some game results.
Okay, sure.
Go ahead.
So we pull up. We have one figure. So you played the centipede game online, and we have the results there, and we can talk a little bit about that and how it goes together with the predictions of Nash equilibrium and of subgame perfection. So in this particular version of the centipede, if you look at your screen, this is the one where it's sort of the typical version where things are increasing exponentially if you manage to get all the way towards the end, but each person has a temptation to stop the game, and the other person's payoff goes down from one step to another. And here you've got the percentages on the bottom of what happened. Actually, the program was set up so it didn't ever get to the last step, because the computer would always grab before the last step. So you didn't actually have a chance to get there. But you can see how many people went down at each step. And it's monotonically increasing, but it's far from the 100% at the first node that would be predicted by equilibrium. And I guess this gives us an opportunity to a number of questions have come up in the forum about rationality, and here I think that's a good illustration of things like common knowledge of rationality, because if you're not quite sure what the other person's going to do down the line, or whether they're going to backward induct, then it's possibly in your interest to try and pass for a while and to see if you can get a higher payoff if you really believe that the other person might pass at least once. So I think that's the logic that goes through people's minds, and indeed, people end up with higher payoffs than they would get from immediately stopping by passing in this game.
This is a good time maybe to say a word about common knowledge in general, and common knowledge of rationality in particular. Mm-hmm. It's not something we're explicitly discussing, although when we discuss Bayesian games, it's implicit there. It's implicit everywhere, really. So there was some discussion about why are players rational, but and why can we assume it? And we discussed it. But we're actually making a much stronger assumption. We're assuming that not only players are rational, so if Matt and I are playing a game, not only are both of us rational, we both know that we're both rational, we both know that we both know it, and so on and so forth. Very, very strong assumption. And perhaps the experimental results of Centipede show us that we want to be careful when we apply game theory in the world. Here, I also have some experimental results. Let me show them to you. Let's say, by way of background, in addition to this online class, I actually teach at Stanford the same class, or rather it's a superset of this class, but the beginning is the same. And what we have about a little over 100 people registered, and physically in class, I think last time there were, I didn't calculate, but maybe on the order of 60. And I just had them play the centipede game, and I did it in 2 ways. First, let me show you the results from one. Well, this won't be nearly as beautiful as the previous graph you saw, but what you see here are, it was a slightly different game. The payoffs were different. There were 5 stages, 4 opportunities to quit, and the payoffs were different, but the logic was the same. As we said, there was sort of a common sense intuition that you ought to continue because the payoffs are increasing, but strictly speaking, a dominant, a subgame perfect equilibrium to quit the first opportunity you had. So what's this? The maximum you could get, I forget what it is, but it was greater than 18. It was on the order of, I think, 25. If you played all the way to the end. So you see that nobody played all the way to the end. Oh, I should tell you what this is about. People got up and repeatedly randomly paired with each other. So people actually got up in class, paired with somebody, played once, and then went and paired with somebody and played again. And so they did it 5 times, and as I say, I think the maximum was on the order of 25. You see that nobody got that, but people did get pretty high. 18 one person, 17 one person, 16 3 people, which means that some pairs stuck around for quite a long time. And in fact, very few, nobody got 0, and only 2 got a total of 1, which is sort of close to the subgame perfect equilibrium. And so this, again, first of all, reinforces the intuition that in reality people play not according to the pristine theory. Also, anecdotally, I asked the people who scored very high what the strategy was, and several of those simply has actually the subgame perfect equilibrium of leaving early, but one had the exact opposite. They always continued the extremely optimistic strategy. So go figure. Also, another anecdote: one person in class, when asked what her strategy was her in this case, said, well, she looked into the eye of the person, and if it seemed like they were about to, if they're a nice guy or girl, she'd go across. So there's that too.
Actually, there have been some fascinating experiments. I think we touched on briefly in the lecture between chess players and students. And when you put grandmaster chess players together, then common knowledge of rationality holds, and they stop on the first move 100% of the time. So every single grandmaster chess player matched with another grandmaster chess player stopped immediately. If you put them together with general chess populations, they passed for a while because they weren't sure. And you put them together with a more general population, and they pass more. So
interesting.
It certainly has to do something with what people are believing the other player is going to do, and you know, that's part of the reason that we get learning over time and convergence. Equilibrium might be limiting points where eventually you become to know your opponents or your population, and then the game changes.
And in fact, in our class, what I attempted to do after they paired randomly and played once with each opponent, with the last opponent, they repeated and played 4 times. Mm-hmm. And the goal was to see whether over time they would converge and be more and more cautious, or and maybe this was too small a sample and not scientific enough, but we didn't see that. Mm-hmm. Because you could also argue that people would learn to develop trust.
Sure.
And
that's a repeated game too.
Yes, exactly. And so, but anyway, so that's repeated games. what else do we want to speak about? There were a whole bunch of issues that came up on the forums, but most of them were dealt with, partly by us, in particular Adrian and Eric.
Yeah, so one thing is if people do see typos somewhere in a quiz or a problem set, let us know. So I think there's one in the OPEC example on the quiz, which was said 667 instead of 627, and that was corrected. But if you spot something like that and it pops up in the forum, then we can fix those slides, and that can be corrected fairly easily. So thanks for pointing those out, and we'll keep monitoring on that. Anything else that...
You know, there are repeated questions about, you know, how can I apply game theory in various situations? Let me read a couple. One was to video or tabletop game design, political analysis, psychology. Another is for network analysis or value chain analysis. Another one, a question on gamification, a sociologist and political science. It's a topic that we can return to every meeting, and maybe let me just pick one of them, and if you'd like, you can pick another. So let's speak about being a computer scientist, about networking. And it comes at various levels. As you know, all computer protocols, in particular network protocols, come at various levels of abstraction. At one level in the stack is the TCP protocol. So how does this work? This is the protocol that governs all transmission of the Internet. All communication is divided into packets. So no matter how large my file is, it's divided into packets, and those are thrown into the network and gets routed according to the IP part. So the entire name is TCP/IP. And what happens is this wonderful, magical thing, self-regulation. So, and this was designed into the Internet from the early days. You send your packets in, and at some point, there's just too many packets in the network, you get congestion, and packets get, as called, dropped. Now, when a packet is dropped, you eventually, you, the originator, get a signal that the packet was dropped. The question is, what do you do with this? And the TCP protocol is very clear. You begin to reduce your rate of transmission. So in particular, as you start transmitting, you start very slowly, sort of arithmetically, increasing your rate of transmission. And as soon as you get a notice of a congestion, you geometrically drop your rate of transmission and start creeping up again. And you get this kind of sawtooth-like picture. And as we see, it works magically. I should say that not all traffic in the Internet is subject to this. Video streaming, in particular this video that you're seeing now, is not governed by the TCP regime, but a lot of the traffic is. Okay, now let's think about it game theoretically. I am a sender, and I get a notice of a drop package. What I want is my transmission to get through. Should I back off? The answer, of course, is no. I should simply keep going. If anything, increase my rate so everybody else backs off and my stuff can get through quickly. And there's some indication that there are rogue implementations that do this, but by and large, people don't do it. But game theoretically, TCP makes no sense, and in fact, it is tragedy of the commons, a prisoner's dilemma, except in real life, it works better than the theory.
Yeah.
Any other examples from your
Sure. So let's see. I've been working on a project studying a series of villages in southern India, and we've been looking at informal borrowing and lending. So, you know, so somewhat like the repeated games we've been looking at. So it's a repeated games kind of application. You know, if somebody comes to you and asks you to borrow money, you have to lend it to them. You're not quite sure they might repay. And in these small villages, they could be asking for a day's wages, a week's wages, a month's wages. And somehow you have to make sure they're going to repay you. There's nobody, it's hard to sign a contract, there's nobody to enforce it. Repetition can help, but also social structure can help. So if you can make it a 3-person game instead of a 2-person game, then having 2 people that could punish you in the future for not behaving. So a grim trigger by 2 or 3 is different, and the more people you have involved, the easier it is to sustain the borrowing and lending. And so that makes very particular predictions about who should be borrowing and lending in which patterns. And then we have data on what these patterns look like. And one prediction is that it's much easier to borrow and lend if you have a friend in common. So if I'm trying to borrow or lend to Yoav, and we both have a friend who borrows and lends with us, then that's much easier for us to sustain that relationship. And so we look at friends in common structures there, and sure enough, you see a strong pattern of this kind of support. And it's present in these kinds of relationships. It's not present if we're just casual friends as much. So it really seems to be tied in some ways to this. So that's another thing where game theory can be helpful in giving you some predictions about what the world might be doing or how it might be behaving, and then we can use those tools to try and see whether we can understand the situations better.
It's interesting, the interaction between games and networks is something that you're an expert in. It's fascinating, especially now with social networks. And the overlay of game theory on top of social networks is a very interesting one. We're not explicitly discussing it, but there are, in fact, we're not at all discussing it in class, but there are models of game theory where the game is played on top of a graph, and there's some special properties that arise as a result. What else should we speak about? We don't have to. Things seem to be going smoothly.
Yeah. Was there anything in particular that came up? I guess the usual Sunday night. There's always a few people who just miss the deadline. So if you try and make sure that you've got the deadlines figured out and not wait till 20 seconds before, then the system will work a little better.
And if you do wait for 20 seconds before, make sure that you're on Pacific time.
Yes, exactly. Make sure your computer clock is correct.
Yeah, there was some discussions about the 50% penalty and various circumstances that make it awkward for people. So we apologize, but with the class's size, we just have to have a regime, and we hope you understand. Yeah. So if you're done, this would be a good time for you to chime in, except we've lost your video. I see you're typing, so you either type or speak. Be happy to have a conversation. If you don't have you, it'd be wonderful to be able to hear you live. Let's try that. But if you don't have it, we'll read your question. And we simply lost your link here. Oh, there you are. Are you comfortable turning on your mic and asking your question in person?
So we lost the rest of the... We only got part of your text of their message. Oh, there we go.
Okay, your mic does not work. Okay, so the question is, the main problem for me is that I studied game theory at the university, but we use matrices, not such applied cases. How is it easier for me to be better in your class? So if I understand correctly, your question is that you find our discussion, well, hopefully still crisp mathematically, trying to make ties with the real world, which is something you didn't see at university, which is purely mathematical. Is that correct? I think you nodded yes. Yes. Well, I'm not sure how to answer this.
Yeah, I mean, I guess there's pluses and minuses to using examples. The plus is that it makes the game theory come to life and shows you a little bit of how these things apply. The minus is that it's always difficult to translate real world into numbers and back and forth, so there's a little more conceptualization that goes on rather than just learning how to read rows of a matrix and compare them. So the theory eventually boils down to the mathematics, and the conceptualization can be difficult. I don't know if there's an easy way to.
It'd be easier to have the conversation if actually your mic worked, but in addition, if I understand correctly, you used a particular formalization within game theory, namely normal form games or matrix games, whereas we're speaking about a broader class of games. And maybe that is also part of maybe something of a challenge that you're experiencing. But again, without having a two-way conversation, it would be difficult to say more. Was this somewhat helpful? We wait eagerly to say if it says yes or no.
Okay, yes.
Okay, our pleasure. Adrian, before we sign off, anything else we're seeing on the in terms of questions? Nothing. Comments on the live stream? No. All right. So.
Okay. Great. So I guess the new videos will be up this weekend, new problem sets, and we're getting close to the end now in terms of the last problem set will be released. So we'll have another Screenside chat, and I guess next week we'll have a special guest to help do the games, and we'll also have some discussion of the auctions. So you can study up on that, and we'll talk about the auction results.
Are you excited about the upcoming final exam?
Oh, very much so.
I am. All right, everybody. Have a good week.
Yeah,
Bye.
take care.